So let me check that one back in the calculator. Type in the thing that we ended up with, negative 1/4, plus the square root of 41 over 4. And I'll store that as my x value. Alright, so now I need to type in the left-hand side, 2x squared. And remember, I'm going all the way back to the original equation. So my left-hand side evaluates to 3.64921841. My right-hand side, with that x value, evaluates to, let's type in negative x plus 5. Exactly the same thing. So everything checks out. You can do the same thing. Go back and type in the other x value. That one was negative 1/4 minus root 41 over 4. Store that as x. And then if I type in the left-hand side, I get 6.85 and so on. If I type in the right-hand side, I get exactly the same value. So both of these check out, both the positive and the negative versions. So that is completing the square. We'll do a couple more of those in class, I imagine. The final solution process comes from generalizing completing the square. So completing the square will always work, no matter what's going on with your quadratic. But depending on what your coefficients are, as in this case, we saw we ended up with a really strange answer, and we had to be very careful with those fractions. It was very tricky, this one. Now, if we generalize this process to the standard quadratic, ax squared plus bx plus c equals 0, then we end up with the quadratic formula. In other words, if I solve this equation for x, I get x equals the opposite of b plus or minus the square root of the quantity b squared minus 4ac. All of that over 2a. And there are mnemonics and little songs. If you Google quadratic formula, I'm sure you'll find heartwarming videos galore of people coming up with different ways of memorizing this. If you use this one enough, you'll probably internalize it after 3 or 4 problems. So that is how we're going to solve the next couple of problems. I'm actually going to go back and solve problems that we've done before using the quadratic formula. So in the notes, under the subsection given over to the quadratic formula, you'll see about 3/4 of the page is taken up with the derivation of the quadratic formula. So I think it's kind of interesting to see where it comes from, and if you can follow along, that's great. This is not something that you'll need to memorize or use often, but it is good to see how mathematics really works. This is real math where we keep reusing a process and we generalize it for future use. So formulas are generally nicer than solving by a particular method. Alright, the equations that we would like to solve. First, we'll go back to one that we solved by factoring. I'll use the quadratic formula. So the way I like to process these is first I want to put it in standard form. This one is already in standard form. We have one side equal to 0 and everything else on the other side. Then I like to identify what are the coefficients. Well, I have a coefficient of 3 for the leading term. I don't have an x term, so the coefficient of the x term would be 0, and the constant is negative 3. So those are the 3 data that I'm going to need when I set up the quadratic formula, which is x equals opposite of b plus or minus square root b squared minus 4ac all over 2a. Now, a lot of folks like to sing that to the tune of Pop Goes the Weasel. Does the trick for them. I will not do that, and I'll spare your ears my absolutely dreadful singing voice. So the Parts we're going to plug in, opposite of b, so negative 0, nothing much going on there. Plus or minus the square root of b squared, so 0 squared, minus 4 times 3 times negative 3, all over 2a, so 2 times 3. So let's clean that up a little bit. Negative 0 isn't doing anything for us, so we can lose that. So plus or minus square root of 0 squared, nothing much there either. Negative 4 times 3 times negative 3 would be negative 4 times 9, negative 9. So positive 36, our negatives cancel there. All over 6. So that's the positive or negative square root of 36, which we'll identify as 6 over 6. So plus or minus 6 over 6, which is positive or negative 1. And this is the first problem that we solved. If you refer back to the beginning of this video or earlier in your notes, you'll recall that x equals 1 and x equals negative 1 were the solutions to this equation. We'll solve this 10th example in the same way. The first step, we want to put this in standard form. So if I move that 2 over to the other side, if I add 2 to both sides of this equation, we get 2x squared minus 16 equals 0. Now one possibility is that we could say that a equals 2 and b equals 0. Again, we don't have a middle term. And c equals negative 16. But I'm going to be crafty. I'm going to divide out a 2. I'm going to factor 2 out of everything. Okay. Now, if I apply the 0 factor property, I'm kind of mixing metaphors here, but you can, as you get more comfortable with these techniques, you can use a little of one and a little of another to pick away at the problem. The possibility here, if 2 times this quantity is equal to 0, then either 2 equals 0 or x squared minus 8 equals 0. Well, I think we'll all agree that 2 equals 0 is not going to be a viable path to travel down, since 2 does not equal 0. Another way to think of this is if I divide my equation by 2, I end up with the resulting equation x squared minus 8 equals 0. So in reality, I could use a equals 1, b equals 0, and c equals 8. Try it both ways. Plug both of these data into your quadratic formula. You should end up with the same answer, but I think you'll find one of them is a much nicer solution process. I will do it both ways. Let's see what happens when we use the first data set. So x equals opposite of b, again negative 0, plus or minus the square root of b squared, 0 squared, minus 4 times a times c, all over 2 times a. So x equals 0 plus or minus the square root of 0 squared, nothing exciting there. Here we've got negative 8 times negative 16. That turns out to be positive 128. We divide that by 4. What are we working with? Well, x equals positive or negative square root of 128. Now, let me see what the square root of 128 is. Turns out to be some never-ending decimal. But 128 is an even number. Let me see if it's divisible by 4. Sure is. So this is positive or negative square root of 4 times 32 over 4. In fact, 32 is also divisible by 4. So this is x equals positive or negative 4 times 4 times 8 over 4. So even better, we could factor a 2 and another 2 out. So x equals positive or negative 4 square root of 8 over 4. Our 4's cancel, and we get the square root of 8, which reduces down just a little bit further to positive or negative 2 root 2. So I went through a lot of steps to get to this result. You may spot those numbers you can pull out a little more quickly. Let's try it with the other set of coefficients, a, b, and c. So if a equals 1, b still equals 0, and c equals 8. We do 0 squared minus positive or negative square root of, that should be opposite of b, negative 0. 0 squared inside minus 4 times a times c. Oh, and that c should also be negative, right? We have a negative 8 there. All over 2a. So you see right away we have nicer coefficients, so this is going to be a smaller solution process. That leaves us with positive or negative square root of negative 4 times negative 8, that's 32, over 2. Don't really need all that. 32 is divisible by 4, so we can pull out a 2. And I'm left with 8. And so we end up with the positive or negative square root of 8 again, which again reduces down to positive or negative 2 root 2. So this particular problem we solved originally by the square root method. That method was a little bit shorter, I think. Solving using the quadratic formula is sort of a nuclear option when the other possibilities, the other solution techniques, might have been a better choice. The beauty of this solution process, however, is that it will always work. So let's try this on one of the quadratics that wouldn't have been quite as easy using the factoring or the square root method. So here we have another quadratic in problem 11, quadratic equation. This one already in standard form, so we can immediately pick out our coefficients. The coefficient of x squared, a, is 1. The coefficient of x, call that b, is 8 in this case. Now we finally have a middle term. And the coefficient, the constant term, the coefficient of no x, is 5. So our solution, x, is going to be equal to 8 squared, plus or minus, sorry, I keep doing that, opposite of 8, plus or minus the square root of 8 squared, minus 4, times a, which is 1, times c, which is 5, all over 2a, so 2 times 1. Okay, let me clean that up a little. We have negative 8 plus or minus the square root of 64 minus 20, all over 2. Alright, well 64 minus 20 would be 44, and this is all over 2. So 44 has a factor of 4 that we can pull out as 2, and we'll be left with 11, all over 2. Now every term here, the negative 8 and the 2 root 11, those share a factor of 2. So I can factor a 2 out of everything in the numerator, be left with negative 4 plus or minus square root of 11, all over 2, and then we'll cancel our 2's and be left with our final answer, negative 4 plus or minus root 11. So this equation was one that we solved by completing the square, and we ended up with exactly the same solution, negative 4 plus or minus square root of 11. We already checked those solutions. They both satisfied the equation, and this is exactly the same place we ended up when we solved this one before. So it's a matter of taste which approach you prefer, completing the square or solving by the quadratic formula. Generally, I think solving using the quadratic formula is shorter. It involves less algebra and more simple arithmetic. So that one tends to be a little more popular. Unfortunately, completing the square will be used for other problems and other types of situations later in this chapter. So we want to make sure that we're capable of solving any of those and that you're comfortable with the process of completing the square, even if when you solve quadratics you default to using the quadratic formula. Now when you're using the quadratic formula, you have the possibility of taking the square root of a negative. So if your x value, remember x equals opposite of b plus or minus the square root of a quantity b squared minus 4ac all over 2a. So your solutions will always look like this. But the interesting thing about it is if the solutions are imaginary or complex, that's going to be caused by some negative value under the radical. In other words, if the quantity b squared minus 4ac is negative, then you're going to have two imaginary, complex, solutions. On the other hand, if that quantity is 0, so if b squared minus 4ac equals 0, then your solution is just going to look like x equals negative b over 2a, plus or minus 0, so there's no additional information going on, and there's only one solution. And it's real. Now finally, if that expression, if b squared minus 4ac is positive, then our solution is going to look like x equals negative b plus or minus some number all over 2a. So we're going to have maybe negative 2 plus 1 over 3, negative 2 minus 1 over 3, giving us two distinct real solutions. Alright, and that is outlined under definition 4.12. This is on the next page under types of solutions. We use that structure to determine whether or not we're dealing with complex solutions or real solutions, and if we have real solutions, whether there will be one or two of them. So in this next section, we want to determine the nature and the number of different solutions to quadratics without actually calculating what those solutions are. So here we see a quadratic equation x squared minus 81. We're going to use the discriminant d equals b squared minus 4ac. And then c is that positive, negative, or 0, and what to conclude from there. So just like with the quadratic formula, I need to know what is a, b, and c. What are a, b, and c? Well, we already worked with this problem before. It's in standard form, so we're good to pick out a as 1, b as 0, and c as 81. And it's negative. Don't forget those negative signs. So our discriminant is going to be 0 squared minus 4 times 1 times negative 81. And our negatives cancel, and we end up with 4 times 81, or 324, which is very positive. And that implies, since what's under the radical in the quadratic formula is positive, that we will have two distinct real solutions. And if you go back to when we solved that problem originally, that was the fourth problem that we looked at by using the square root method, those solutions were x equals 9 and negative 9. So we weren't looking for those, but we know that what they are, so we can confirm that we came up with the correct conclusion by looking at what those solutions actually were. Okay. Again, here we have a quadratic already in standard form. If your quadratic equation is not in standard form, you will need to do the additional steps to put it in its standard form. In other words, get one side equal to 0 before you can tell what A, B, and C are. So here we have A, 20, B, also 20, and C, 5. So our discriminant is going to be B squared, 20 squared, minus 4 times A times C. Now, I'm not going to go to the calculator for this one. I'm going to use a little bit of tricky arithmetic and say 20 squared minus 4 times 5 would be 20 times 20. In other words, we're saying 20 squared minus 20 squared. And any number minus itself is 0. So if the discriminant is 0, we conclude that we're going to have one repeated real solution. And if you refer back to that problem, that was number 3. We solved that one by factoring. Our repeated real solution was x equals negative 1/2. Remember, we came up with two resulting implied equations whose solution yielded negative 1/2. So that's not what we're trying to do here. We're just trying to figure out what type of solution and how many we should expect without actually calculating it. But we know that there was only one solution to this problem back when we solved it earlier in the section. So on this last problem, we'll do the same technique, but I have a ways to go before I can figure out what the pieces of the discriminant are. I need to write this in standard form, which means I need to multiply out 2x plus 1 squared. So this would be negative 5. Now, a common product of binomials, for example, something like 2x plus 1, if I square that, I'm going to get the square of the first term, 4x squared, plus 2 times the first times the second, so 4x plus the square of the second term, 1. Okay, if I multiply that negative 5 through, I see negative 20x squared minus 20x minus 5 equals 25. And we'll go one additional step. I want to get one side equal to 0, so I'll subtract 25 from both sides. So negative 20x squared minus 20x minus 30 equals 0. So I'll use those coefficients. A equals negative 20, B also equals negative 20, and C equals negative 30 to determine the discriminant. So D equals B squared, negative 20 squared, minus 4 times A, negative 20, times C, negative 30. Okay. Well, 20 squared, if you plug that in all into the calculator, you'll end up with negative 2,000. Well, that is very much less than 0, so this equation is going to have two distinct complex solutions. If you refer back, this was the 6th problem that we looked at. We solved it using the square root method, and we ended up with those two complex solutions. So refer back to that one and confirm that our conclusion here is correct. So that is what the discriminant is used for and how we would calculate it and interpret the results. Now the final idea that I'd like to look at in this section is that of the solution by graphing. So again, I'll go back and I'll look at 3x squared minus 3 equals 0. Now, when we put a quadratic in standard form, or indeed whenever we get one side equal to 0, we can think of the left-hand side as a function. We're saying f of x is determined in this way by this formula on the left. When is f of x equal to 0? Well, it's equal to 0 at its x-intercepts. So if we graph f of x, if we graph 3x squared minus 3, and I'll use a standard zoom, then if we know where the x-intercepts are, then we know the x values that satisfy the equation. So if I calculate the zeros, and I'll find the left-hand 0 first, I'll go a bit to the left, a bit to the right, and my guess is somewhere around -1. X equals -1. That is one solution to the original equation. The second solution, I can calculate that 0 by going a bit to the left, and then a bit to the right, and then guessing. The other solution is at x equals 1. We already knew that, we've already solved this problem, but you can also do it using the grapher. Now our second equation is going to take a little more work. We want to write this in standard form, so I could write this by adding 2 to both sides as 2x squared minus 16 equals 0. And I'll plot that graph instead, 2x squared minus 16. And there we see another nice parabola. If I calculate the 0 furthest to the left, I'll go a bit to the left, it looks like it's around -3, so I'll go over to -4 or something. Come back a bit to the right, somewhere in the middle. Turns out x equals -2.8288427. Now that is a really strange looking number, and when we solved this algebraically, we came up with x equals the -2√2. So if you plug both of those into your calculator, you'll end up with the same approximation. If I calculate the other 0, left bound, it looks like it's crossing somewhere around 3, so I'll say my left bound is 2, my right bound is 4, and my guess is 3. Well, it's actually 2.8288427, which corresponds with the positive 2√2. So we can come up with these approximations using the calculator. Sometimes if our x-intercepts or our solutions are nice round numbers, it won't make a difference. But if we're looking for an exact solution, we're going to want to use one of our algebraic techniques. Now our final equation here, remember this one had 2 complex solutions. Let's see what that would look like in the grapher. Well, again, I first want to get this equal to 0 on one side so I can look for x-intercepts. So if I subtract 25, what I really want to graph is -5, 2x plus 1 squared, minus 25 equals 0. So let me plot that function, -5, 2x plus 1 squared, minus 25. And my calculator's working, and it's done working, and I can't see anything. Well, if I go to the table, I can tell some of the points on this graph. So when x equals 0, my function's y value is -30, and it just gets lower from there. So -30, -70, -150. Let me zoom fit, see if that helps at all. Okay. So that's a little bit extreme. I can't really see the x-axis. Let me see what window we're working with. Well, my y min is -2230. That's excessive. Let's go down to negative, let's say 200. My y max is negative, which means I can't even see the x-axis. I'm entirely below it in this window. So let me go up to 100. And my y scale, since I'm going in hundreds, let me change that to every 25 units. Okay. So we have a pretty extreme window, but now we can see our graph. And notice, if I were to plot this, my graph appears to lie entirely below the x-axis. In particular, there are no x-intercepts. So the relationship between the location, the existence of x-intercepts, and solutions to the associated equation, if there are x-intercepts, those are those x-coordinates, those zeros, are solutions to the equation. If there are no x-intercepts, it's because there are no zeros, there are no solutions to that equation, at least not in the real numbers. So this equation has solutions, but they are complex. And we're going to have to find them using some other approach. We can't use graphing in the real plane, real x values, real y values, to find complex x values which solve our equation. But this is kind of another test. If you graph your equation and there are no x-intercepts, then you know you should be looking for complex solutions, kind of like if your discriminant were negative. That's the situation that you would be in. So those are all of the techniques. Go ahead and get started on those homework problems. Bring any questions that you have to class.